Yeah, well, this is the last topic we're going to discuss. Determinants. Yes. Well, it's a very powerful... What happened? It is a very powerful thing if you know how to use it. I'll show you a few ways where it is so useful. But first we have to learn the way how we can compute this quantity. So determinants, it's a numerical quantity you associate with a square matrix. So they do not exist for any other matrices, they only exist for square matrices. And for every matrix you come up with a number, and it's a number which is called determinant. There are two effective ways of computing determinants. In fact, the most effective way to compute the determinant when you combine these two ways in a smart way. But first we will look at them individually, these two ways. First one, I call it computing via minus, and I'll explain it first. This is something we briefly touched when we discussed with you the cross product of vectors at the very beginning of this topic. So first notations for a square matrix. You see it is a square matrix, n times n. It's two symbols which people normally use to denote this number, determinant, either that a or they put something like an absolute value, but it is not an absolute value just because it's the symbol a. This symbol a represents a matrix. So when you compute them via minus, determinants are defined recursively. So you define first the determinant for the matrices of size 1, then matrices of size 2, size 3, and so on, depending on the previous one. So for size 1, determinants are as easy as the simple number, because matrix of size 1, it's a number. For the matrix of size 2, general matrix of size 2, like so, we have a direct formula. And here it is. You multiply the entries across the main diagonal, like this, and then you subtract the product across the other diagonal, like this. For the higher orders, here the recursive formula will kick in. For instance, if you look at the case n equals 3, when you look at the case n equals 3, is a general case of size 3 times 3. When you look at such case, you do this thing. People call it a row or column decomposition of a determinant. I will show you first a row version of this decomposition. What you do is this: you choose a row, and this time I'll choose first row, this one, and you start doing this geometric procedure. You pick every element in this row. For instance, you pick the first one, and you cross out the column and the row where this element sits. You see, I crossed out this column and I crossed out this row, and this minor, or the remaining part of the matrix, this is something which is called minor. So by choosing an element in the matrix, any element, in fact, I can choose this element, for instance, and by crossing out the rest of the elements in the same column and in the same row, see, this one is gone. Sorry. This one is gone, this one is gone, this one is gone, and this one is gone. The remaining part, if you assemble it in its own matrix, which will be matrix of size 1 less, this new matrix, it's called minor. And the determinant of this new matrix is also called minor. Or sometimes there's another way, people sometimes call it also algebraic complement, but it's not so often used in this topic. Because by crossing the row or crossing the column, you end up with the matrix of size 1 less. Here's your basis for the recursion. You can use the formula for the determinants of the previous size. For instance, if you look at the matrix of size 3, by crossing a row or column, you will end up with the matrix of size 2 times 2. For that, we have a direct formula how to compute the determinant. And now you combine all of this like so. Look at this. You choose a row or a column. Like I said in my demonstration here, which is still hidden, I chose first row. Look at this. is my first element of the first row. So I copy the element, A11, and I multiply it by the determinant of the associated minor. So here's the associated minor. So I multiply by the determinant like so. Then I move my cross to the next element of my row. I copy this element of this row. Almost copy. There's just extra negative here. I'll comment on that in a second. I copy this element in here. I cross out all of the other elements in the same row and the same column. The remaining elements of my matrix, if you assemble them into a matrix, that would be a matrix of size 2 times 2. And the determinant of this smaller matrix goes as a next factor in your decomposition. Finally, you move your cross to the next element of your row. You do the same procedure. You copy the element. You copy the minor as a determinant. And that is finished row, first row decomposition for the determinant of size 3. Each of these individual determinants, you can now evaluate them via this formula. You will end up with a number. You do all of the arithmetic, and that will be the result, the resulting determinant for my 3 times 3. Signs here, when you do this row decomposition, on the top of what I just described, you also have to do alteration of signs. So the first element comes with plus, the second comes with minus, next one comes with plus again, if you do it for the first row. And that is how it goes for the row decomposition. Sometimes you can also do the column decomposition. For instance, you can use this element, and this element, repeating the same process, picking up this remaining of the matrix, the minus, and factoring them by the elements and doing the sign alterations. You will end up with the same. It's not an easy result actually that you will end up with the same number by itself. It's a beautiful result in fact, because the procedure itself is very complex. Being able to, inside this really complex procedure, being able to see this tricky way of identifying this procedure for row and for column, you have to be very smart to be able to do that. Well, one day you probably will see that, but it's a little bit beyond what we do here. Yeah, in fact, not only you can use column, not only you can use the first column, you can use any other column or any other row. And every time it will deliver the same number. Think about that. It doesn't matter which way you do this procedure. You can use, for instance, second row, so this element with this minor, this 2 and this 2. I will show you this computationally a few times later. Then this element with the remaining elements here, A11, A31, A13, A31, and A33, sorry, and this element. That will be the decomposition, which corresponds to the second row. In that case, you will, when you do sign alteration, in that case, this first element will come with the minus. In fact, I don't have it here on this slide, but actually I'll tell you this. When you do row or column decomposition, when you do that, there will be an element, there will be a minor. Signs, when you determine which sign to put next to your term in your decomposition, the best way or the universal way to proceed is this. You take the indices, so for instance, if you have a term like this, if you have a general term of your matrix A, J, K, somewhere in the middle, like in here, the sign which you put next to it, you determine like this. You take -1 and you raise it to the power j plus k. So you sum up the indices of the element, and if the sum is even, then the sign will be plus. If the sum of the indices is odd, then the sign next to the term will be minus. This is a very general way to describe this sign. It works here, because for instance here, you see we put plus in front of this term, and the sum of the indices here, 1 plus 1 is 2, even number. The sum of the indices here, 1 plus 2 is 3. That's why we got negative here. Here we got 1 plus 3. Sum is 4, even number. That's why we got plus. So if you do your row or column decomposition with respect to any other row different from the first row or the first column, your sign alteration will follow this pattern. Remember this. The rest of the just resembles whatever. Now, in fact, on this slide I have the general version of it. I'll open it. It's quite a bit of, well, it's a lot of symbols to copy. So if you have a general matrix of size n times n, and if you choose first row for the decomposition, for your computation of determinant, you pick an element, you cross the rest of the row, you cross the rest of the column. My cross is not long enough, but this one is also crossed out. The remaining bit, this one, will be minor, and that is the basis for your decomposition. That's how I put it here. Look at this. I use this capital A's with the index 1, 1 to abbreviate this minor, because I don't want to copy this again. In fact, it's a standard notation for that. Next, we'll go with the minus. So when you move your cross here, second element in the first row, and then this one column and this remaining bit underneath, it will be the content of your minor, and that's the name for that minor, A12. You have many terms like many other terms like this. The one before the last one, this one. The one before the last one. You see, even here, when I put my sign alteration, I use this pattern. Because the sum of the indices here, no, I didn't use this pattern. Because 1 plus n take 1 is n, actually it's a typo. And the last one in your expansion or decomposition will be like so. And again, we have a typo here. I'm surprised this. Because the sum of the indices here, 1 plus n, or n plus 1. Remember, well, that's this, like I said, this capital A's, this is just the abbreviation. You can say JK minor. Yeah, so this is the minor associated by the JK element of your matrix. So the matrix, if you cross that element from your matrix, the remaining parts will compose your minor.